In this video, we're going to look at parallel vectors. And the reason for that is when we focus on calculus ideas, it's going to be important for us to recognize when two vectors are pointing in the same direction, even though they might have different magnitudes. And that's not going to be something that's necessarily immediately obvious from the component form. Let's take a look at these two vectors here for an example, where we have v equal to 1, negative 2. So positive x and then negative 2y. So we would have that as our vector v. And then w is 2, negative 4. So if we start here, we'd go over 2 and then down 4. And we would see very quickly that w is in fact parallel to those two. They're parallel amongst themselves. Let's try that again. We would see that v and w are in fact parallel. The challenge is, could we have detected that or noted that before we actually drew the vectors? We don't want to have to draw everything. We would like to be able sometimes to just look at the component form and decide if that's true or not. And in particular, what if we had something that was not parallel? If we have 1, negative 2 versus 2, negative 5, well, that would go further down and that would break this parallel structure between the two vectors. How do we know that without getting to the diagram? Well, what most people notice first is that these two vectors here, 1, negative 2 and 2, negative 4, are multiples of one another. Whereas 1, negative 2 and 2, negative 5 are not multiples of each other. And that is the key observation. If we look at the components from 1 to 2, okay, I scale it up by 2, and from negative 2 to negative 4, I scale that up by 2 as well. So it's the same multiplier for both the x and the y components to translate from one vector to the other. That doesn't work when we look at the scenario down here with 1, negative 2 and 2, negative 5. Here we capture that in notation. If two vectors are parallel, then there exists a scalar multiplier that we can slide in here that turns one of my vectors into the other vector. How does that work in terms of symbols or identifying whether a vector is parallel or not? Well, let's go to 3D because that's already more challenging to work with. And what we're looking for is to show that there is a C value such that 3, 4, 5 is equal to that constant times 1, 2, 3. Well, what we can do is look at the components of each of those expressions, and we'll have 3 equal to C times 1. Or if we look at the y components, we would have 4 on this side equals C times 2. Or in the z component, we would have 5 equals C times 3. And the question is, can we find a C value that makes all of these happen? And I think the answer pretty clearly and very quickly is no, because to satisfy the first equation, we have to have C equals 3. However, to satisfy the second equation, we'd have to have C equals 2, and we can't satisfy both of those at the same time. Both can't be true, or both can't be satisfied with a single C value. And if that's the case, then we conclude that these vectors are not parallel. 3, 4, 5 is not parallel to 1, 2, 3. For comparison and reference, if we went back a slide and looked at these two vectors, we would see that w, which is 2, negative 4, is actually equal to 1, negative 2 if we slide in a multiplier of 2, which would be our C value. In that case, we would have been able to find a C value that satisfies one vector is a multiple of the other.